is similar to Lab 12, but in this case we work with load and store instructions. So the objective is the same, trying to understand how these instructions are executed by the processor. And we analyze different scenarios. We analyze the loads to a low latency memory, to a DCCM, stores to the DCCM, and high latency loads and store to the external memory. These loads and stores to the DCCM just do not stall the processor, because latency of these memories is just one cycle. Instead, when we have to read or write, to read from the main memory, we have to wait for the data to return for several cycles. Thus, we have to stall the processor. Well, there's the option of non-blocking loads. This is analyzed in the lab, but not here. Here, I will only show you the first case, low latency loads. So this is the example that we have. We place the data that we want to read in the DCCM. We explain in the lab how to do that. And then we access that data. That data is simply an array of two components, and we are reading the first component here, the second component here. And we surround them by NOP instructions, include them in an infinite loop so that it's easier to find them, and analyze a random iteration of the loop for one of these instructions. And we obtain something like this. So this is the load executing, the second load, this one, which computes the address by adding T0 plus 4, and then reads the value and places it in T1. So we have the load executing here. This is the load instruction. And these are the base address and the offset, right? This is the base address, F004 and 4 zeros. And this is the 4 that we have to add to the base address according to this instruction. So we decode the instruction in cycle I. Cycle I plus 1, we compute the addition of the base address and the offset, obtaining this address, F004, 0004, which is the addition of these two numbers. And see that we enable reading of the DCCM. Why is that? Because this address is within the range of addresses mapped to the DCCM. Okay? So the hardware will enable reading of the DCCM. So in the next cycle, we are provided with the read value, which is an 8. Okay? This value is propagated and written back in this stage. This would be the write back stage, written back to the register file to register 6, which corresponds to T1. So that in the following cycle, we see how the register changes its value. Okay? And again, we provide this figure explaining all the units traversed by this instruction and the signals that are related with the execution of this instruction. So we have the instruction in the decode stage. It's decoded. It generates several control signals. And also it has the offset. And this is the register T0, which is read. So this is the base address plus 4. We do this addition in a specific adder at the DC1 stage, which is the same, which is associated with, or to the EX1 stage. We obtain this address. This address makes the read enable of the DCCM go high, so that DCCM is read. It provides the 8, which is propagated and written back to the register file. Again, the names of the signals are the same as the ones used in the Verilog file. We do similar analysis for stores and also for loads and stores accessing not the low latency memories, but the external memory, which has a high latency. Okay? Lab 14 starts dealing with hazards. So we start with structural hazards, then lab 15 is about data hazards, and finally lab 16 is about control hazards. Structural hazards, we illustrate two situations where we have to deal with structural hazards. First one is a unit conflict. When we have two instructions in the same cycle, which arrive at the decode stage in the same cycle, the second one must wait because we only have one multiplier. Okay? So there's a structural hazard there, which is resolved by making the second instruction wait there and only execute in the following cycle. The multiplier is pipelined into 3 stages. So when the first mul instruction goes to the second stage, the second mul instruction can go to the first stage of the multiplier. Okay? Hardware cost and performance degradation are low in this case. And we also analyze a second structural hazard that takes place in the register file. And in this case, 3 instructions arrive at the write-back stage in the same cycle. Okay? In a two-way processor like SWRF-H1, 2 write ports should be enough in the register file. But there's a situation that can make 3 writes happen in the same cycle. That's because load instructions can be non-blocking, meaning that independent instructions can continue while the load is waiting for data to come back from the external memory. And at some cycle, the load will receive the data and will want to write to the register file. But at that time, 2 other instructions may have arrived at the write-back stage and want to write to the register file too. Okay? So we have 3 writes to the register file in the same cycle. One solution would be to provide only 2 register ports, 2 write ports in the register file, so that one of the writes would have to wait. But a better solution performance-wise is to provide 3 write ports so that the 3 writes can happen in the same cycle. And that's the solution used in SWRF-H1. So in this case, we can see in the simulation, which is provided in an example, we can see that the 3 writes can happen in the same cycle using the 3 write ports available in the register file. Okay? Unfortunately, we don't have time for showing this situation. I'm only showing the first one, where we have this artificial program as usual. We have 2 mul instructions that we force them to arrive at the decode stage in the same cycle. We surround them with NOP instructions as usual, and we obtain this Verilator simulation where we can see that in cycle I, the 2 mul instructions arrive at the decode stage, but given that there's only one multiplier, the second mul instruction will stall in that decode stage and only start executing in the following cycle, cycle I+1. So results will be obtained sequentially. Note that we have multiplication of 3 times 2, obtaining 6, and 2 times 2, obtaining 4. And these are written to the register file, again, in 2 consecutive cycles. Okay? So I'm asking you now to replicate this situation, and as you will see it in Verilator, but also using the performance counter. So this project is prepared for being able to measure instructions and cycles using the performance counters. That way you can find the IPC obtained by this artificial program. Before doing that, please remove the NOP instructions, okay, which are only used for the verilator simulation, and then measure instructions and cycles, and you'll see that IPC is not ideal. Ideally, we'd obtain an IPC of two instructions per cycle. But given that the second mule will have to wait, we'll lose some time in that, and we won't obtain the optimal IPC. And what I'm asking you to do is to reorder the code so that you can obtain the optimal IPC without obviously changing the code functionality. Okay? You have it guided in the document, but maybe in this case it's better that we do it together. So I'll be doing this, or at least the initial part, measuring with the performance counter so that you can see it and then replicate more easily in your laptop. So let's open, first of all, well, let's close the previous project, and let's open folder the lab 14 mule instruction project. Okay, you'll see that there are several projects there showing the different situations analyzed in this lab. We want to open now mule instruction project, available in lab 14. Okay, so we open this. This will contain the program that I've just shown in the slides. Here it is. You can, well, it's. Yeah, here it is. So we have the two mule instructions surrounded by NOP instructions. If you generate the trace, don't forget to update the absolute path of the verilator binaries. I already have it here, but you will need to update it. Okay, so we generate the trace. Okay, my path is not correct either. Now it is. It's generating trace, and so if I go into lab 14, mule instruction .po build Schwerwolf, and I open the trace with GTK wave, you will see that you have a TCL script that includes the signals that we want. So read TCL script. In the mule instruction project, you'll find a test.tcl file that you can open, and this will show the signals. So let's go to a random iteration and zoom into it, and you will see that you can see the same results that we had before. And this is the first part, replicating the verilator simulation. The second part is to run the program on the board and measure with the performance counters instructions and cycles. So if you now upload the program, upload the bit stream to the FPGA, I have it here.
You took the knobs out. Okay.
No, no, I didn't. I should have, but I forgot. Thank you. So I should have done this. Well, okay. And so now, if I run the program on the board, and I open the serial monitor, you see that in the C program we have we are measuring cycles, instructions, and multiplications committed. And when I run till the end, well, this is not an infinite loop, okay? It's a loop that repeats for this number of iterations, okay? 100,000, around 100,000. And so this is the number of cycles, and these are the number of instructions. If you divide instructions by cycles, you will see that it's not 2, it's 1.75 or so, okay? Because the second multiplication is waiting for 1 cycle. So please try to replicate this and then reorder the code so that you try to obtain the optimal IPC.